So to determine what is the best choice and what are the most adequate thicknesses, we have carried out and developed computer code totally written in MATCAD latest version 14, and determine for each wavelength what's the best thickness combination, either for palladium gold bilayer or gold single palladium layer. And this curve shows the maximum reflectance change of palladium gold combination, let's say, as a function of wavelength for the best thickness. So this curve means that you have an angular scan of the reflectance, and you find the point of maximum reflectance change due to absorption of giving the optical properties changes of Röntgen and Rubin, and we calculate that to simulate that the maximum reflectance change. And these are the curves we obtain. And these are the thickness that gives this maximum reflectance change. In all simulations for this type of combination, the gold was converged to the lowest, let's say, thickness value established by the computer procedure, and palladium was obtained. This thickness here, this thickness of palladium was obtained, and here we have a thickness of a single palladium layer and the maximum sensitivity, and we can see that the maximum sensitivity occurs nearby 900 nanometers, and well, it's 910 for a single palladium layer, 930 for gold palladium, and the sensitivity is slightly better for the single palladium layer. And so this is, I mean, we cannot differentiate one relative to the other here, one thin film configuration relative to the other one here, because they are quite similar. If you look at the angular dependence of reflectance, they are not on the same horizontal scale, but we can infer here that for instance, the gold palladium layer is more sensitive to wavelength changes. The single palladium layer is not. The maximum sensitivity is for the single palladium layer. And also, if you go from here to 45, approximately to 50 degrees, we have a reasonably large, let's say, change in maximum sensitivity. If you look at the same situation for the palladium, single palladium layer, you don't have that much change. So the single palladium layer provides a slightly larger sensitivity, is less sensitive to wavelength change, operating wavelengths, and also is not too sensitive to this setting wavelengths. If you want to make a device that operates at a single wavelength, if you have an error, a design error, I mean, that's not going to cause significant loss of sensitivity of the device. So that's the choice after all these simulations. Single palladium layer. This is the wavelength calculated at the optimum wavelength of 920 nanometers. We have made some experimental measurements. We have a homemade computer-controlled reflectometer that operates at 975.1 nanometers. The reflectometer has 4 stepper motors, all of them computer-controlled, so I can make arbitrary rotations in small steps, controlled by the computer. As the rotation takes place, there's going to be deviation of the input beam due to refraction on the prism. This deviation will change the footprint of the laser beam on the sample. It's going to move to a different position, and the computer has an algorithm that automatically corrects that and puts the footprint back on the original position. So we have that. We can translate the sample into directions, and we have a translation stage also computer controlled that sets the diode, the photo detector, the signal photo detector at the maximum response. So we can make an experiment, just press a button, just program the experiment, press a button, and have the whole curve. This photograph shows just the gas delivery system that we have. We still don't have a way to control the relative concentration of hydrogen in the sample. We just have a fixed concentration of hydrogen at 4% in a mixture with 96% of hydrogen, and we have pure hydrogen, so you can switch samples and see the effect on the palladium surface. This is a mount that we fabricated for this, and we have our palladium films already sputtered in the physics department at Federal University of Pernambuco on glass slides, and our prism is a BK7 prism. These are the results for the differential reflectance, that is, the reflectance after exposure to the gas subtracted to the original reflectance. This is for a reference, so because we only have at the most 4% of a mixture of hydrogen, and our theoretical prediction is calculated for 100%. We have put those two curves together for a comparison. We cannot linearize the theoretical curve measured at 100% by Röttgen and Rubin down to 4% because the way the optical constants change with the hydrogen concentration is non-linear, and we cannot linearize down here. So we're just putting those two curves together to compare their shape and see how far we are from the maximum theoretical, let's say, limits. So this is for a thickness of 7.7 nanometers. That's the operating wavelength that we have in our system, and that's the result we got for that. We have also made a study to see how successive recycling of the hydrogen and nitrogen gases, switching of the gases, what does it cause on the refracted signal at a fixed wavelength, at the one that gives the maximum reflectance change, right here, 43.34, for this particular wavelength and thickness. So this is nitrogen, so we put hydrogen, a mixture of hydrogen with nitrogen, we have that exchange. Then we replace the sample, and we have that back and forth. We have a rise time typical of 10 seconds, and we characterize our maximum noise at 0.002. So this is clearly, I mean, this something is the thickness of this line gives the noise approximately. But you can see here that we have some loss of sensitivity of the surface, or perhaps some hysteresis. And we have to look that up with more detail in future experiments. It appears that the sample starts to lose sensitivity as it gets exposed to air, but we haven't done any long-term aging, let's say, experiments to determine that. We are in the process of doing this study to determine what's the most adequate thickness